Hi all, and welcome to 6.6. 6.6 is DeMoivre's theorem. It's the last section in the chapter. It has a lot of information, so you might need to buckle up. I will try and get through it as quickly as possible for you so that you're not sitting there watching a super long video. It's not super difficult, but what it's going to do is DeMoivre's theorem puts together polar form or trig form and complex numbers and points on the coordinate plane, and it kind of combines everything together for you. And then when we're using polar form for complex numbers, turns out that there are some properties that polar forms of complex numbers have that rectangular forms don't, that will allow us to perform computations way faster. So it's great, and it's a fun section, and I'm sad that I don't get to see your faces while you learn this, because you'll be amazed, I'm sure. Okay, so here we go. Here's complex numbers revisited from before. Remember, if we were graphing a complex number, we would graph it on an arcgan diagram, which means like the real number part of it would be on the x-axis and the imaginary number part of it would be on the y-axis. So if I was graphing the point a plus bi, then the x distance here would be a, and then the y distance here, or the imaginary distance, right, would be b, and this would be the complex number. Z would be that point on the complex number plane. So if that's true, then let's go ahead and figure out which it is. Let's figure out how that relates to polar form. Well, I know that the modulus of Z, which is how far away the number is from the origin, would be the square root of a squared plus b squared. But then we're like, yeah, but wait, isn't that the same as the length of r if r was a vector? And isn't that just the same as writing it without those brackets? And so that would be r, right? R, which is the radius away, is the modulus of z, which is kind of cool. And then if we throw a theta in there, we've done before, and it should be on your paper plate already, that a, which is the x coordinate, ends up being r times the cosine of theta, and b ends up being r times the sine of theta. When we did this before, we were doing it with x and y, but okay, same thing, right? Just using different letters. So what we're going to do is we're going to write this complex number z in trig form by substituting what a and b equal in there. So a would be r cosine theta plus bi, well, b would be r sine theta. And so this is now how I can write a complex number, but notice that the characteristics that I'm using to describe it are r and theta instead of a and b. So a and b would be the rectangular way to describe the complex number, but r and theta would be the polar way or the trig way to describe the complex number. And so this, z equals r cos theta plus r sine theta times I, is the trig form of a complex number. We can make that look a little bit prettier. Here you go. Here's the official from the textbook. So this is a little bit prettier. They've factored out the r, and they threw the I in front of sine theta so that it's not ambiguous whether we're taking the sine of theta I or what the coefficient is. Turns out that then, because we're going to be working with this quite a bit in this section at least, that we want an even better abbreviation for this. So we're going to, r is r, and then instead of cosine theta plus r I sine theta, turns out that you can actually write that as cis theta. And this is not, cis is not some other trig function or something like that. It stands for those two terms, cosine theta plus I sine theta. Cosine theta plus I times the sine of theta. And so that's what our cis theta represents. You can write it out entirely every single time that you want to do it. I think that the textbook writes it out. It doesn't use the r cis theta abbreviation. I'm going to abbreviate it because this is so much easier to write, and it is a legitimate mathematical abbreviation. It's not something that I'm making up, by the way. Okay, so a couple examples of finding the trig form of a complex number. So we're going to start with the one on the right here. We're going to do the trig form of 3 plus 4i. You don't need to draw a picture, but I'm going to draw one anyways. So this would be 3 and then plus 4i, right? That would be how I would plot that on the Argand diagram. And so the radius of this would just be 5 because of the Pythagorean theorem. And then the angle, I'm going to use the other formula on the paper plate that says that tan of theta equals the y divided by the x, which is going to be 4/3, to get that theta is approximately 53.130 degrees. Remember, sometimes you're going to have to add 180 degrees or pi radians to get to the correct theta if your angle is in quadrant 2 or in quadrant 3. So in this case, 3 plus 4i in rectangular form would be equivalent to 5 cis 53.130 approximately degrees. These are just different forms of representing the same complex number. So that's just like in Algebra 1 where we were doing writing the equation of a line, and we used slope-intercept form, and then we use point-slope form, and then we use standard form. They all represent the same thing, it's just different ways of writing it. Okay, for the one on the left, to find the trig form of 1 minus root 3 times I, we can do it the same way that we just did the first one, but if you notice that this is very similar to one of the points on your paper plate. On your paper plate, you have a point at 1/2 negative root 3 over 2. And sorry. So if we were looking at that, notice the 1 minus root 3 is the same thing. It's just a scalar multiple that both of those components have been multiplied by 2. So 1/2 and negative root 3 over 2, we know is the angle negative pi-thirds or 5 pi-thirds. We can say 5 pi-thirds if you want. And so because it's a scalar multiple of 2, we know that on the unit circle, this radius is 1, but each of these numbers is 2 times what the coordinate on the unit circle is, which means that here the radius is 2. We can also do the Pythagorean theorem to see that the radius is 2, like we did in the first example, right? That we can take root 1 squared plus negative root 3 quantity squared and get the square root of 4, which is 2. So it's fine to just do it the algebraic way. I just wanted to show you that if you recognize that it's on the unit circle, it saves you that work. And you're like, yeah, but look, it's just radius of. Also then, if you recognize that it's on the unit circle, then you don't have to say tangent theta equals negative root 3 over 1. We can simply just find that location on the circle and say, yeah, that's 5 pi-thirds. And so we know that the trig form of this number would be 2 cis 5 pi-thirds. Or you could say 2 cis negative pi-thirds as well, and that would be okay. So here are the properties that I was alluding to at the beginning of the lesson. Complex numbers have properties, right? Have their own set of properties. So like you know that I squared is -1, etc. But if you write the complex number in trig form, then they have some more properties that you didn't know about. So if Z1 is R1 cis theta 1 and Z2 is R2 cis theta 2. So the subscripts are just to denote, right, to differentiate Z1 versus Z2. It's not, those are not squared, they're not exponents, they're just subscripts. So then we would multiply them by multiplying the radii, so R1 times R2, and then adding the angles, cis theta 1 plus theta 2. And this is amazing, and I'm not going to give you the proof for this, you could maybe look it up, but you can just take my word for it, and that it's true and that it works, and that's why we love math. And then using that, you should be able to figure out what Z1 divided by Z2 would be. I'll give you 4 seconds to think about it. Okay, so hopefully you thought, well, dividing is the inverse of multiplying. So instead of multiplying the radii, I will divide the radii. And then instead of adding the angles, I'll subtract them because that's the inverse of addition. And so that would be Z1 divided by Z2 would be R1 over R2, cis quantity theta 1 minus theta 2. Let's do some practice. The numbers here, Z1 and Z2, are not written out in, or they are written out, they're not in the abbreviated form. The textbook I don't think uses the abbreviated form, so I wanted to show you what you're going to be used to seeing. You are welcome to just simply write that as 10 cis negative pi fourths. And you can go ahead and write Z2 if you want as 4 cis pi thirds. So then if I wanted to multiply the two numbers, I would just say that Z1 times Z2 would equal 40 cis, and then I would add those angles, negative pi fourths plus pi thirds, which means, yep, common denominator. So this would be 40 times cis of, and then negative 3 pi 12ths and positive 4 pi 12ths would give me cis of pi 12ths. And so then that would be the answer. The problem was given to us in trig form, so we can answer it in trig form as well. You don't have to multiply all that out and convert it to rectangular form. If I wanted to divide the two numbers, I would say Z1 divided by Z2 would be 10 over 4, which is 2.5 or 5 halves. And then I would subtract the angles, so negative pi fourths minus pi thirds. And then I'd get 5 halves, cis, again with the common denominator, right? That would be negative 3 pi 12ths minus 4 pi 12ths, and that would be cis negative 7 pi 12ths. Okay, ta-da, moving right on. What if I wanted to multiply z by itself? So instead of z1 times z2, I wanted to multiply z times z. So if z squared is simply z times z, and I already know the rules for multiplication, right? That this is just multiplication here. And so if I was just using those rules, then wouldn't I say that that's r cis theta times r cis theta, which would be r times r, and then you'd add the angles together, which would be theta times theta, or theta plus theta, which would be 2 theta. So it turns out that z squared is simply r squared cis 2 theta. And you don't need to write that down if you don't want. This is just kind of conversational. We're building up to something. How would we calculate z cubed? Same thing, we're building up to something here, right? So z cubed is z squared times z. And I already just calculated z squared. But z squared was r squared cis 2 theta. So I'd have r squared cis 2 theta times r cis theta. And then what would I do? I'd multiply the radii and I'd add the angles. So that creates r cubed cis 3 theta. And then I'd like you to stop for just a second and see if you could make a conjecture about how this pattern would continue and what z to the nth power would be. I'll give you 4 seconds. Turns out that if you have thought of anything or discovered anything, that if you correctly did it, then you discovered the same thing that DeMoivre discovered, which is that if z equals r cis theta, and then the second part just means that n is a positive integer, is within the set of positive integers, then z to the nth power equals r to the n cis n theta. So the radius gets multiplied by itself n times, and the angle gets multiplied by whatever n is. And then I'm going to write this for you in the abbreviated form over here. If z equals r cis theta, then z to the nth power equals r to the nth power times cis n theta. It's just easier to write that way. And so I'm going to give you an example of how we can use this and why it's way better than not having it. Okay, so if I were to ask you to find 1 plus I root 3 quantity cubed, the old way of doing that, like before today, if I had said find that, it's not that you couldn't find it, you could, it would just be a big pain. we would do 1 plus I root 3 times 1 plus I root 3 times 1 plus I root 3. So let's go ahead and start distributing. This would be 1 plus root 3i plus another root 3i, so that would be plus 2 root 3 times I. And then I root 3 times I root 3 would be 3i squared. But we know that I squared is -1. So then this actually gives us 1 minus 3, which would be -2, plus 2 root 3 times I. The I is not inside the square root. Sorry that I didn't write it in front of it. And then I'd still have to multiply it by another 1 plus I root 3. So let's go ahead and do that. So I'll FOIL that, and I get -2 times 1 is -2. Then I get plus 2 root 3 times I here, but I get minus 2 root 3 times I there, and those actually cancel out. And then for the last terms, I would have I squared, and I'd have 2 root 3 times root 3. So 2 root 3 times root 3 would be 2 times 3, which is 6, right? So plus 6i squared. That's -2 minus 6. So it turns out that when you cube that complex number, you actually get a real number, which is kind of cool, that you get -8. Okay, but here's the new way to do it. The new way says, let's write this number in trig form. So if we write 1 plus root 3i in trig form, again, you'll notice that that's a scalar multiple times 2 of the point that's on your unit circle at pi thirds. So this is actually a radius of 2 and an angle of pi thirds. You're welcome to use the formulas if you don't see that off the top of your head right away, but I just wanted to show you that converting is not that big a deal if it's on the unit circle. So if this is the polar representation of the complex number, then if I want to cube that, then that's just 2 cis pi thirds cubed. And then DeMoivre's theorem says that that's 2 cubed times cis of 3 times theta, right? So 3 times pi thirds. Well, that's just 8 cis pi. And then let's think about what that means. Doesn't that mean 8 times the cosine of pi plus I times the sine of pi? Sorry, started writing theta instead. There you go. And then isn't that -8 because the cosine of pi is -1 and the sine of pi is 0. And so look at that, I get -8. Some of you may be arguing that the old way was still easier for you. Maybe, because the new way is new. Also, we were only cubing it. What if we were taking it to the 17th power? Then I hope that you would agree with me that the new way is going to be way better. Okay, so that is taking a complex number to a power, right? The last topic that we have in this section, so thank you for hanging in there. I know it's a lot of material and a long video to watch, so my apologies. The last topic that we have would be to find the nth roots of a complex number. And so the textbook gives you this that says a complex number v, they're just defining it to be v, a plus bi is an nth root of z if v to the n equals z. The example I can give you with real numbers to make it make way more sense is 2 is a cube root. I'll go ahead and write it out for you. 2 is a cube root of 8 because, or if, right, 2 cubed equals 8. And that's pretty much what that top sentence is saying, but it's saying that that's true for complex numbers as well. The second little piece of information here is that if z is 1, if the number that you're taking the roots of is the number 1, then we can call whatever those roots are roots of unity. So if I want the cube roots of 1, then I would say the cube roots of unity. It's just a little vocabulary thing to keep in mind. Okay, so let's go ahead and do a couple examples. Find the cube roots of -1 and then graph them. Ooh, okay. So you already know 1 cube root of -1, that if I had asked you this before today, you would have just said, oh, look, the cube root of -1 is -1. That's true, but that is a hidden, that is simplified, right? Because you were little Algebra 2 students and you didn't know any better. Turns out that if we're looking for cube roots, that there are going to be 3 cube roots of any complex number. There are going to be 5 fifth roots of any complex number. There are going to be 16 16th roots of any complex number, etc. So here's where it gets fun. So we would say if we're trying to find the cube roots of that, then that means z cubed would equal -1. So I'm going to write both sides in trig form. So that would mean r cubed cis 3 theta equals, and then what's -1 in trig form? So think about that. -1 would be -1 plus 0i. And so the angle there, if you just think about where that would be, that would have a radius of 1, right? It's 1 unit away from the origin, and it's at the angle pi. So far I haven't actually done anything except to rewrite the left-hand side and the right-hand side both in trig form. But now I can equate the parts of this. So I can say r cubed then has to equal 1, which means that the radius is 1. And then I can say, if I look at the angles, I can say, okay, then that means that 3 theta would have to equal pi. And so theta equals pi thirds. So that's one answer. That's one of the cube roots of -1. To get the others, there are a couple ways you can do it. One is to say if there are 3 cube roots, they all are going to be equally spaced around the circle. And you'll see what I mean in just a second. The other is more algebraic, so I'll show you that as well. Don't tune out, like you focus here, you'll get it, I promise. So this 1 cis pi that represents -1 is one value that could represent that, right? But remember, I could slap as many full circles on that as I wanted to, right? Like I could say that that was 3 pi or 5 pi or however many pi. So if that is actually pi plus 2 pi k, then if 3 theta is pi plus 2 pi k, then that means that theta, I would divide all of these by 3, right, both terms, and I would get theta equals pi thirds plus 2 pi thirds k. And that means that each angle is 2 pi thirds apart on the circle. In this case, it is the unit circle because r is 1. Sometimes it's not the 1 unit circle, it could be the 3 or 4 unit circle, whatever. But in this case, it is the unit circle. So I'm going to go ahead and draw my circle over here. I have that one of my answers, right, I had was r equals 1 and theta equals pi thirds. So I'll call my roots z1, z2, and z3. So the first one that I found was 1 cis pi thirds, and then so that would be up here. And then I'm going to add 2 pi thirds until I can just keep going around the circle until I can find the 3 roots that should be equally spaced. So if I add 2 pi thirds to that, then that means the second root would be 1 times cis pi thirds plus 2 pi thirds, which is I, which would be right here. And z3 would be 1 cis and then add another 2 pi thirds to that, and I would get 5 pi thirds there. And so those are my 3 roots, and you can see that they are equally spaced apart. And then, because the problem was not given to me in polar form, the problem was given in Cartesian form or rectangular form, we should go ahead and rewrite these in rectangular form as well. And that's just evaluating them, distributing, knowing that that means cosine of pi thirds plus I times the sine of pi thirds. So the cosine of pi thirds is 1/2 plus I times the sine of pi thirds, which is √3/2, but I'll write it in standard form, so I put the I afterwards. 1 cis pi is just the -1, and then the sine of pi is 0 and it goes away. This is the one that I already knew, right? When I said, oh, look, the cube root of -1 is -1 up here, that is this one. So it is an answer. I just found it now by the super cool method. And then 1 cis 5 pi thirds would be 1/2 minus √3/2 times I, because those would be the coordinates of 5 pi thirds on the unit circle. Okay, I know that was a lot of information to take in. Luckily for you, you can rewind that and watch that as many times as you want. That's an example of finding the roots of a real number, right? I mean, -1 is a complex number because it does fit into the complex number set, but it's more specifically a real number. And so I wanted you to have a chance to find roots that were also of complex numbers. So let's find the 4th roots of this one. This will be our last example for the day. So if I'm looking for the 4th roots of this, first I'm going to just write it in cis form. So this would be 5 cis pi thirds. And I'm not going to do all of the setup work that I did with the other one, because I hope that you can see then that this is how we can try to make it a little bit faster when we're going through these problems. So if this is your number, well, let's not call it z, let's call it v, because I'm calling all of the other numbers z. So if I'm calling z to the 4th equal to 5 cis pi thirds, then I could write z in trig form like I did last time, and then I could equate the radii and I could equate the angles. Or I could go ahead and say, yeah, but I'm going to want to do the backwards of what DeMoivre's theorem is. So I'll want to take the 4th root of the radius, and I want to divide this angle by 4. You can do it that way as well without showing all of the work. It's up to you. I'm going to go ahead and put the plus 2 pi k on here so that I can find all of my angles and not just one of the roots there. So remember, z to the 4th is r cis theta. Look, I am going to write it out for you anyways. R cis theta to the 4th, which is r to the 4th cis 4 theta. So then when I equate the parts, I get that r to the 4th equals 5, which means r would be the 4th root of 5. We're just going to leave it like that. And then theta, well, 4 theta would be pi thirds. And then remember that cis pi thirds is the same as cis pi thirds plus 2 pi k, because the cosine and sine values would be the same if I added 2 pi or any multiple of 2 pi. So that means theta would be pi 12ths plus 2 pi 4ths k, which is pi halves k. And so this tells me that I have my 4 answers now. I have z1 would equal the 4th root of 5 cis, and then pi 12ths, because I'll just let k equal 0. That's my first one. Z2 would be the 4th root of 5 cis, and then what does it say to do? It says, well, let's add pi over 2. That if there are 4 roots, they're all pi over 2 apart on the circle. And then let's make a common denominator. So that would be 6 pi 12ths, and that I'll add to the pi 12ths and get 7 pi 12ths for the next one. Z3 would be the 4th root of 5 cis, add another 6 pi 12ths, and I'll get 13 pi 12ths. And then Z4 would equal the 4th root of 5 cis, let's add another 6 pi 12ths and get 19 pi 12ths. Since this problem was given to me in trig form, I do not need to calculate the cosine of pi 12ths and I times the sine of pi 12ths and distribute through. I can leave the answers here in trig form, which are right here. I also want to graph these so that we can talk about them in a little bit more detail. We're gonna minimize that a little bit. Okay, so if I graph these, notice that I'll have, this is not the unit circle, by the way, this is the circle with a radius of the 4th root of 5. But either way, it doesn't matter, it's a circle nonetheless. And I would have pi 12ths for my first angle, and then 7 pi 12ths, 13 pi 12ths, and 19 pi 12ths. So you can see that those are all pi halves apart, right? That these would all be right angles here. And that they're all equally spaced along the circle. Also then, last but not least, you can see that because I was finding the roots of a complex number, these are all equally spaced apart, but they don't have symmetry other than rotational symmetry. But if we are finding roots of a real number, you'll notice that the roots themselves, when graphed, will not only have rotational symmetry, but they will also have symmetry over the x-axis, that they'll have x-axis symmetry, which means that every complex root of a real number comes with its complex conjugate. You may want to write that down. I'm not going to, but you may want to write that down. Every complex root of a real number comes with its complex conjugate. And you can see that here, that we had 1 plus root 3 halves, or 1 half plus root 3 halves times I, and then 1 half minus root 3 over 2 times I. That those came with their complex conjugate. -1 isn't a complex root, so it didn't come with its conjugate. In this case, they don't come with their complex conjugates because the number that we were taking the root of wasn't a complex number to start with, not a real number. Okay, so that's a lot of information, but I think that that is going to be sufficient for you to go ahead and do your 6-6 homework. So don't stress out too much, and I hope that you enjoyed this section. Goodbye.